Yeah, welcome to EuroSciPy. So it's the second day of the tutorials. We have here Tim Hoffman, who is the core developer of matplotlib. And actually that's, the person who knows it in depth. And you're happy to be here today to learn from him about the basics of matplotlib, right? And please welcome Tim. And if you have any questions, just raise your hand. I'll come to you and give you the microphone because we are recording the session. So it's better that your question stays on the record.
Okay, thank you. So Artem already announced me. I'm Tim Hoffman. I work for Zeiss in the semiconductor division, and basically we are making the machines with which you make computer chips. So basically all the computer chips in your laptop are made on our machines. If you want to learn more about that, we're a sponsor of the conference. You can come to our booth next to the main hall. Apart from that, I'm a matplotlib core developer, so there are multiple of them. I'm not the only one, of course. And just as a reminder, we are an open community, so if you have any suggestions how to improve the library, or if you see only some typo in the documentation, we really encourage you to take part and collaboratively improve the library. So today's tutorial is about the core ideas behind matplotlib. And what I would like you to learn is to understand the principles and how you use matplotlib to make your plots, your visualizations efficiently. This is based on Jupyter notebooks. You can find them on GitHub. You can download them now and follow along, but there are not too many things that you have to do interactively, so it's not necessary because it's more about the concepts and less about doing things yourself. There are some small parts where you could do things yourself, but given the time, I likely skip over them and you can do them afterwards. Okay, so let's do that a bit larger. Is that large enough for all of you? Okay. Matplotlib is one of the major visualization libraries in Python currently. There are multiple of them. Matplotlib was the first one. It's dating back to 2003. Nowadays, there are also other ones, like in particular Bokeh and Plotly, and there's a whole visualization ecosystem. Depending on your needs, one or the other is better. No of these tools fulfills all needs, but to give you an idea why matplotlib is maybe still relevant, matplotlib is very flexible. It's designed to basically be able to plot all things you can imagine. Because it's around so long, it's basically available in every installation of Python. So you don't have to specifically check for that dependencies. Usually it's just there. It's a basic library on which other libraries have built on top to, for example, for more specialized kinds of plots. So like geographic plots or statistical plots or financial plots, because you cannot just have a reasonable library which can efficiently, with a few commands, do all the plots. So matplotlib provides the basic plots and building blocks out of which you can make more targeted, also domain-specific plots. And matplotlib can be used in various backends, so you can create various graphic files. You can use it in notebooks. You can embed it in graphical user interfaces. And it's the default plotting backend, for example, for pandas. And there's, even if you don't write new matplotlib code yourself, it's likely that you encounter visualizations by other colleagues that already use that. So having a good understanding of the basics of matplotlib will really help you to get your visualizations done. So as said, matplotlib dated back to 2003, and it was actually developed by John Hunter, who was a neurobiologist and who was at that time using MATLAB for his visualizations, and he realized that MATLAB was not capable of the things he needed to do, for example, interfacing with databases and providing visualizations via web servers in their labs. And that's why he started to look for an alternative. And back in that time, there just was no alternative, so he started to develop matplotlib. And because he was coming from MATLAB, some of the design decisions he did were just, I tried to copy MATLAB behavior and MATLAB interfaces. And in some parts of the library, you still see that, which may sound a bit foreign nowadays because some of the paradigms in MATLAB are quite different from how you would do things in Python. We try to move away from the MATLAB things, but because compatibility is also a great concern to us, so we are very careful about not breaking existing visualizations. These things are still around, and that's sometimes a source of confusion because there are 2 or sometimes even 3 ways to do things. And I also try to explain to you what you nowadays should use and what you shouldn't use. Okay, so getting started. If you're in a notebook, probably the default one is you want your visualizations to appear in the notebook, and that you can achieve with the inline directive. So, this is actually a command from IPython. This just makes sure that matplotlib can send the graphics to the notebook. If you work in Python applications, if you have a Python file, of course you don't use that. You just use the normal import, which you already also have to use in the notebook. And the simple thing you can do is you create your basically drawing canvas. I come to that in a moment, what that means, and you plot your data to it. If you're in a notebook, at the end of such a cell, the plot will automatically be shown. If you want to show it explicitly, you would have to call show, which you also would have to do if you're, for example, in the command line or in a Python application, you want a window to pop up. But this show is implicit in notebooks at the end of a cell. So we can save that. If we have such a plot, there's some basic elements or terms you should understand. The first one is the figure, which is the outermost container of your visualization. It's sort of, you can think of it as the drawing canvas you put everything else on. Then you have an object called axis, which is the container for a single subplot or single plot, so one coordinate area. So if you look at the visualization here below, the blue one is the figure, and the green one is the axis. And it's a plural object. I think this terminology also comes from matplotlib, and because it's plural, it means it's just not one direction, but it's the whole area. And that includes also some things like the scales. So these two are the main building blocks you will always see and use. Additionally, but that's just a little bit less important, but just that you heard it, we have the singular axis, which is a direction with a scale. So it's not the line here or this line, but it's the direction with the mapping of some logical data coordinates to physical screen coordinates. And then you have the spines, which are just these lines. The spines, you can deactivate them or move them if you want to. Yeah, and in general, you likely don't use that directly, but probably you see it in different places in the documentation. We have a term called artists. Artists are all visual elements. So every entity that's somehow represented in your plot is an artist. So these texts are artists, the figure itself is an artist, an axis is an artist, and so on. So the basic usage pattern, if you start with matplotlib, is you create a figure, your drawing canvas, and you create one axis, which is your coordinate area. After that, you draw the data into your axis object, into your coordinate area, and optionally you configure further parts of the plot, like putting axis labels. So we can see that in this example here. You create the figure and one axis object, and there are different ways to do this. The most convenient one, if you just need one, is to have this subplots command, which creates both the figure and your coordinates at the same time. And then you have the axis object, and you can call methods on that, and there are methods to add data to it, for example, this plot. And there are other methods to configure further properties, for example, here the axis labels. Okay. Now we switch to the discussion of the interfaces, which is often a source of confusion and which stems back to the MATLAB similarities and origins. Essentially, currently we have two different interfaces, two ways you can work with matplotlib. The first one is the so-called axis interface or object interface. This is already the thing we have seen, where you literally create a figure and an axis object, and you have variables referencing them, and you work with methods on these objects. This is the most general form of using matplotlib, and it's basically suited for everything. When you plot in a notebook interactively for simple and for complicated plots, you definitely should use it when you use matplotlib in a script or a library. So if you're not the end user of your code, but somebody else, because then because you're holding on to these variables, you have full control of your plots, and you don't interact with other plots. Then there's the pipplot interface, and the pipplot interface is basically just a pure function interface. So you don't have an explicit variable holding the figure and the axis. They are still there, but they are somehow in the background. And you just have functions which operate on these background objects. You have the notion of a current figure and a current axis. You could have multiple of them and have explicit commands to switch between them, but if you have more than one, that really gets confusing. So pipplot can be used if you just have very simple plots, because you just basically save the need to explicitly create your figure and your axis. If they are not there, they're automatically created in the background. And you can use it in a similar way. So you see here I created these explicitly. They are not here. The figure and the axis are, if they are not there, with the first command, matplotlib will create one automatically for you if you use just this function-based interface. Even though we call this the pipplot interface and the axis interface, the first call to creating your explicit figure and axis is located in pipplot, so don't confuse that. Even though, and that has technical reasons, you always start from there. The difference in way of working is, in the first case, you only use the subplots and maybe show from the pipplot subpackage, and everything else is explicitly on the objects. Whereas if you work on the pipplot interface, you only have the functions and you don't take any explicit figure and axis objects. There's one additional historic interface, which is still there for backward compatibility, but which we really recommend not to use actively, and that's the pylab interface. Pylab was originally designed to be even more like MATLAB, and in MATLAB you don't have any namespaces. So the way of using in pipplot was to just from pipplot import star. So you have everything in your top level namespace. You can just write plot, ylabel, ylim. This is exactly how it would look like in MATLAB. This has some major disadvantages in Python. For example, this wildcard import not only imports plotting functions, but it imports a vast number of NumPy functions as well. For example, NumPy sum, which overrides your built-in Python sum function. In some edge cases, the NumPy sum function behaves different than the built-in Python sum function, and that can lead to really subtle errors. So this interface, not using namespaces is not a good idea in Python. Don't do it. Always use either this pipplot interface with a prefix or go to the axis interface. Yeah.
Oh, it's green. Okay, I have a question, Tim. So often in my practice, I see people mixing two things. So for example, I see that they create a figure and axis, but at the end of that cell, they usually call plt.show, but not figure.show. Can you comment the difference between the two?
Yeah. So figure.show is basically, I think we have it in the documentation right now. The problem is that for the visual backends, you like popping up a window. You need to have an event loop running, something managing the interactivity with the window, and this is also for historical reasons only available in the pipplot submodule. It's tied to that. We plan to move it out of there, but it's quite difficult to get it out. And if you call figure.show, you still get the figure, but it's probably not responding to you. There's, if you want to look further into that, this is the warning message. The short answer is, in 99% of the cases, don't use figure.show, but use the plt.show. You're on the safe side with that. And if you're in this axis world, these are really the only two commands, maybe three if you use safic, but safic you can use from the figure interface as well. So basically, if you're in the axis interface world, plt subplots and plt show are the only two commands you directly use from the pipplot namespace. Okay, so if that was all very confusing about different interfaces and you don't want to learn too much, the recommendation is just go with the axis interface, so the first one I showed you, because you can do everything with that and you're on the safe side. The other one is just the convenience if you work very interactively and you want to save some characters and typing quicker, then you can use that as well if you know what it's doing in the background. And actually, there's a direct translation between these two worlds. If you have functions that add data, they are exactly the same as access method and as pipplot functions like plot, like bar, and all the other functions that add data. If you want to modify parameters on the access objects, you have all the set something methods, for example, set xlim, set labels. And in pipplot, you just don't have the set, because in pipplot is modeled after how it's done in MATLAB. And in MATLAB, you set a property just by calling a function with parameters. If you want to get values back the other way around, on the access interface, you have the corresponding get methods. And the historic MATLAB way of getting a value is calling the same function without arguments. So if you know these, you can easily translate between the two worlds. And yeah, this is a bit of a more complicated example, but essentially you see that all the axis plot are, this is the second example, but yeah, given the time, you can try that later out. Just after the tutorial, just take these ones, take these rules, and transfer it to pipplot. And there's another one in reverse. Okay, so let's look a bit closer into how we can create figures and one or more of these subplots. What we've already seen, if we just need one plot, the trivial thing to do is, yeah.
So you said to use axes instead. You said to use axes instead of the pipplot thing.
Yeah.
But the first thing you do is import pipplot.
Yeah. That has technical and historical reasons, because pipplot is not only the interface, pipplot is also the engine of managing the figure is a part of pipplot. It's a technical detail which is hard to change. We are planning to separate these things, but it's for historic reasons it's that way. And so the pragmatic answer is don't think about the name pipplot interface too much. If you want to use access, there are two functions, which are plt subplots and maybe plt show. These are the only two functions from the pipplot namespace you need, because they get you started and finished. And in between, you don't care about pipplot. Okay, so this is the simplest way to get a figure and an axis object. You could also make that all by hand and wire it up, but this is the subplots function is the convenient interface to get your figure and your axis. What this does, it returns a figure and an axis object, and yeah. These are instances of the respective classes. You can have multiple of these. So if you want to have two plots side by side, you can specify rows and columns. When you do that, what you get in return is still a figure, but instead of a single axis object, we now get a NumPy array, apparently, which seems sort of weird. The basic idea behind the NumPy array is that it's a container into which you can index. And we see in the next plot that if you take, for example, 2 by 2, this has the nice property that you can have multiple indexing. And this is basically almost the only thing why it's a NumPy array, because it was, at that time, it was the simplest thing to have 2D indexing without having double brackets with nested lists or something like that. So basically, you don't have to care that it's a NumPy array. The only thing you typically want to do with this is take it as a container where you can have one, or depending on how many subplots you have, 2 indices. If you have only 2, it might be more handy to unpack your 2 axes into explicit variables. This means this is now an axis object and this is now an axis object, and I can directly work on them. This saves me the effort of typing the square brackets AX0, AX1 in the following plot commands. So this is quite handy. If you have 2, you can do it if you have 4, but then again, it's starting to get unwieldy, and you definitely want to unpack if you have more than 4. But what you can also do if you have a whole bunch of them, NumPy has a flat iterator, which just gives you one axis after the other. And with that, you can also modify all your subplots without explicitly having to address them individually. If you don't have a regular grid, but want to do some more complex layouts, since a couple of versions, we have Subplot Mosaic, which is inspired by the patchwork library in R. And what this does is I provide a 2D list of elements. This is a grid of names, basically. And what I get back in return is, so first what I configure with that is, you basically, this 2D grid makes up a grid of your drawing space, and if you have names repeating, the plots are joined to a larger one. For example, we have this right top here, we have this right bottom here, and because they are both called left, they are joined to one plot. And what you get with that is now here a dictionary, which you can index with the names you have used to create. So this is a very handy one if you have more complex layouts. There are some variants of that. There's a shorthand notation if you have more complex layouts, for example, something like this. If it's getting more complex, having these 2D lists with long names is maybe not so handy anymore. You can have a compact notation where you have just single characters defining the same thing. So this area here where you have A, this corresponds to this plot. Then the B up here is here, and the D is below here, and the dot means leave out that area. And you can configure your plot with that. And the corresponding dictionary now has these A, B, C, D entries where you can plot into. And there's a lot more you can configure. As in most of the functions, if you go to the help, there are a lot more things you can do with that. Okay, so just to give you a very high-level approach, these are the two most common ways to create layouts of your subplots. There are other functions, and I've tried to come up with a complete list and sort of a guidance which functions you use to generate which layouts. So you have the subplots for a single figure. You have subplots with rows and columns for a regular grid. You have the subplot mosaic with for more complex layouts. There are a lot of other historic functions which you likely won't ever need. There are earlier approaches to making more complex layouts, but the Subplot Mosaic API is much simpler for these cases. You can also have inset axes. You can have twinned axes where you share the x-axis and have two different y-axes, say one type of data associated with the left side of your y-axis and one type of data associated with the right side of the y-axis. And you can also, if this is all not enough, you can also place individual axes anywhere you like in your figure. So then let's have a look at the figure size. The figure size is somewhat historically given in dimension of inches, but it sort of still makes sense because you don't have a universal measure for figures or for dimensions because we're not only plotting to pixel backends. Then you could say I want to have 100 times 300 pixels or something like that. But for example, we can also write to SVG or to PDF or also other vector backends, and that means there's no notion of a pixel necessarily. And therefore, we have this abstract length dimension, and you can leave that out. You can translate that. So the standard dots per inch for matplotlib is 100. So if I say I have a figure size of 6 by 4, that means 600 by 400 pixels on pixel backends, and this is probably the way you want to think about it. So if you have a size, it's scaled by the DPI, and with that, you can adjust your figure size. If you adjust your figure size, you're making your plotting area smaller and larger. Is that a question? So you're making your plotting area smaller and larger. So this is a figure size of 8 by 4. The same plot with a figure size of 4 by 2, which means it's only half the height and width. But all the fonts, this one and this one, they are not affected by that. So it's just making your paper larger and smaller, but not changing your font sizes. Yeah.
They have the same size. Show it again. Why the second one is so much more?
Because here I set figure size 8 by 4, and here I set figure size 4 by 2. Oh, sorry. Sorry, this is just the text domain. Yeah, thanks. Okay. Then we have the topic of layouting. So if you plot a lot of additional information, like here, very large numbers with the label on top, by default, matplotlib does not do any layouting, like shifting around things so that they don't overlap. But we have layout managers you can activate for that, so they are just in fixed positions initially. And maybe you have seen Tight Layout, which is a very basic layout manager. It's been around for a long time. Since now already a long time, the Constraint Layout manager is in there, and if you activate that, you just type layout constraint, then everything is shifted properly. And likely for more complex plots, you want to use that.
What's the difference?
The difference between?
Tight and constraint.
Tight layout is a very simple heuristic solver which tries to move some things around. The constraint layout solver is a more rigorous approach where you say, I have all the elements and they have fixed sizes or they have variable sizes, and I solve an optimization problem to move them all in correct places. So it's in the background, there's happening much more. If you have very complex layouts, and if you want to update them very often, that can sometimes become a bit slow. But for just static plots, that's not an issue.
Tim?
Yeah.
Before we go to another one.
Yeah.
Once I had to create the figure, which is A4 paper format, and I had to put multiple axes into this figure.
Yeah.
And it was a bit a nightmare to align those because I used the put axis method. And because, well, if you add some note or if your footnote is becoming kind of huge, the plot is messed up a bit, like the figure. Is there a way to evenly distribute multiple axes on the A4 figure somehow? Like you create a figure, you set the dimensions, and then what I want to put, for example, 4 axis objects in that figure, evenly distributed from top to bottom.
So but shouldn't that basically the subplots do? Or what's not working with using subplots for that? Because that creates a regular grid.
Correct, but sometimes I want one to be bigger, smaller, whatever. Like the same as you showed on the third here, when I have like one big plot, one small plot. So I want kind of this behavior.
You could use that, or you couldn't use that then? I don't know. I don't understand exactly what's...
Yeah, maybe that answers.
Maybe we can discuss that afterwards.
Yeah.
Okay, now we have our basic layout of figure and axis. We have a closer look at adding data to your plot. We've already seen that in the introduction. We do that with some methods. And the most used one is plot, which plots your data as a line or as individual points, depending on the additional parameters. But it's basically a y versus x plot. Just as a note, many of your matplotlib functions return a value. You often don't need them. Sometimes you can do some things with the objects, these artists that are created. So plot returns the line object that's representing here this data. If you are in a notebook and you don't want to have these outputs, a convenient way to suppress that is to put a semicolon at the end. Then you don't have any noisy return values that you don't use. Yeah. So if you a lot of matplotlib functions returns the artist that you created, and you have this output value here, which you basically most of the time don't need and maybe don't want because it's just noise in your visual notebook. So you can add a semicolon at the end of the line, which suppresses the output. I leave this in here. Okay. With plot, there are 2 ways you can change your style and color. There's one simple MATLAB-based format string, which is quite handy if you just want to have some very rough, quick layout adjustments or visual adjustments. This is an optional 3-tuple or 3-component string of a marker, and the marker can, for example, here be this O, this X, and in this case we don't have a marker. The order doesn't matter. Then you have character for the line, or maybe multiple, so it can be this is a line, this two dashes is a dashed line. You can have a colon for a dotted line, and you can have an optional color, which is, in this case, it's green, and in this case, it's red. These are very basic. If you want to look them up, they're documented. Where is it? Here they are documented at the bottom of the plot function. So here are the markers, the line styles, and the colors. This is, in case you have used MATLAB before, this is exactly how you do it in MATLAB. This is a very, yeah?
So how can you easily integrate, for instance, like hex colors, or because I saw only like a number of 10 colors there. So how can you customize the color if you want to give it like a hex code, for instance?
Customize the color?
Yeah, because now, so the page you showed with the documentation has like those 10 colors probably.
Yeah.
So can you do some more?
Yeah, I come to that.
Okay, great.
Okay, so this is really the shorthand version. It's probably you use that if you have some data you want to have a quick look and you see by default we have a line. If you say I need to see the individual data points, I can just turn that into points or points with the line, and this is the shorthand to just see and configure your data. If you want to do it more exactly, you have keyword arguments. So then you don't use this shorthand string notation. You have keyword arguments which have much more power. You can do much more things with them. And you can basically reach the same. Sorry. Did I do? So you can make your.
That the previous one it has no. When you're missing values, show the previous one. Yeah. That.
Yeah.
Like that.
Yeah.
Where do you specify the color of
the color. So yeah. So the question was, I did not specify the color here, but apparently there's a color, and the color is actually determined by a color cycle or a plot cycle in the background. We also come to that. If you have multiple elements plotting on top of each other, there are some defaults. So the general comment on this, there are some defaults, and the defaults can be iterated also. So they are not necessarily constant.
What I mean is that the order, for example, the next one you show the color and then the pattern.
This one?
Yeah.
The order doesn't matter. So it doesn't matter if I write green X or X green. So this is the same one. This is really just a very basic shorthand notation. You just have to know I have red, green, blue, for example, RGB, and I have X and O for markers, and I can just put them in any order in the string because you don't want to remember the order. Or the third one is the line style, which can be solid line, dashed line, or you can have here a dotted line, for example. If you think this is complicated, you don't have to use that. This is a shorthand notation that's inherited from MATLAB. You can use it to very quickly adapt your visualization in the sense I've shown here above. But if you want to have full control, you anyway should move to the keyword arguments. And we have a color cycle. So if you plot multiple lines into one axis object, you see that the color is automatically cycles, which sort of makes sense because you want to still be able to distinguish your data. By default, we have 10 colors in the color cycle. So you see that here the blue one and the orange ones are repeating. So you go through that cycle, and if you have more, you're just repeating that. But you can configure that color cycle. You can also configure marker cycles and other things there as well. For specifying colors, that was also somewhere a question up there. You have, if you use the keyword syntax and also in other parts of the library, you have various ways of defining colors. So you have this short one-hand notation with red, green, blue, black, white, and cyan, magenta, yellow. You can have common color names written out. You can have hex notation. You can have an RGB tuple where red, green, and blue values are always between 1 and 0. So this is purely red. You can have a string floating number, which seems a bit weird. But what this does is encoding shades of gray. So if I do 0 here, I would have a black line. If I do 0.9, I would have a very faint gray line. So this is sometimes quite handy that you have different shades of gray readily available. And you have a whole large range of colored names from the CSS4 standard. You can look them all up here. So basically almost every color you can think of and name is accepted here. There's one specific one mentionable, which is this CN notation. CN means take the nth color from the color cycle. So in this case, it's C1, so I take the second color from the color cycle. And this can be quite handy. For example, if I want to annotate my plot here, I know I plot one data set and I plot a second data set, and I now want to add text with the respective colors. One way to do that would be to take the line object, extract the color and set that in here. The second way would be to go into the color cycle and ask the color cycle what was the first object, what was the second object. But the convenient way to do that is to say, just give me the first and the second color from the color cycle, and I can use that to encode my or to make the texts the same color as the lines which they are referring to. So you have, as said before, you have return values, and when you plot, what you get is here, in this case, a list of line objects, because you can have multiple data sets plotted simultaneously in here. And if you just have one 1D array, you just have one. And you can access the individual elements and style them later if you need to. Typically, you don't need, but there are cases, for example, in the end, I will show you an animation example where that can be handy. That you can have access to these underlying objects and manipulate them later on. because this returns a list, this plot command returns a list of line objects, it's often handy if you have to access individual elements that you use tuple unpacking. So instead of putting it into a variable, which is then in the end a list, and indexing into that, you can automatically unpack the list into a tuple, and because it's only one element, the tuple is defined by having the semicolon at the end. So you could write it like this to make it more explicit, but the defining element for a Python tuple is the colon. So, and if you do it like this, then you have the line object directly at hand. You can instead, what we've done so far is directly putting in the data values, mostly NumPy arrays, but can also be lists, for example, into the different x and y parameters. What you can also do is if you have something that's indexable, so something which you can index by square brackets, and that can be a dictionary, that can be a structured NumPy array, that can be a pandas data frame, that can be any arbitrary user-defined object which supports index access. Instead of doing plotting and writing data this, you can just give the names and give the object into which to index by a data keyword. For 2 parameters, that's maybe not that clear and efficient that you need it, but if you, for example, plot it with error bars, or if you plot scatter plots where you can also configure color and marker size depending on your data, you have multiple parameters, and then it can be more handy to give just the data object, and instead of giving numbers here, just give the names with which to index into the data object. So now we come to legends, and by default, legends work this way. You can add labels to your data. So here I added a label to the data I added via keyword argument. And if you then call legend, you get a legend with all the elements that have a label set. You can also set it later, of course. So if I would just leave that out here, I would only get a label for the first one. So the legend automatically looks up which elements are in the plot and which have a label, and they are added to the legend. It can sometimes be more handy to do that explicitly, and in that case you need the objects. So here in this example, I want to have the one legend for both of the subplots. And you cannot do that with a pure legend call, because the legend just works on the axis object, and that would mean this axis doesn't know about any data in here. So the automatism doesn't work, but I can explicitly save my line objects here into variables, and then don't use the automatic detection of labels, but just say I have these objects and I want to have them to have these names, and put them please in the legend, and it's the legend here in axis 2. So you can do that explicitly. And there are a lot of configurations, as with all matplotlib functions. For example, you have keywords to specify where the legend sits and how large the text is, and so on. That's the very general case, that you have some reasonable defaults, and if you want to configure them further, there are keyword arguments to do that. Yeah, just to give you another simple example for another plot, because we have just seen the plot command. Bar plots are done by bar, and by default you can have bar plots based on numbers, but more often than not you have some labeled data you want to plot, and instead of giving numbers you can just provide the labels on your x-axis, and what that does is there's still a coordinate system in the background, so you can overlay that with other data. And I just to show you, the labels are positioned at integer positions. So what we've had here is this x is 0 to 1, 3, and just to show you here that I plot the markers here at 0 to 1, 3. They are on top. So you can overlay this categorical data with other data you have. And there are a lot more plotting functions. The one reference to go to is on the matplot types overview. You see a lot of things you can plot. They all basically work the same way. They are methods on your axis object. They take data parameters and optionally a lot of keyword arguments that you can use to configure your data in more detail. And we don't look into these because the pattern is exactly the same as I've shown you for plot and for bar. The second handy point of reference is the Axis API. And here you find all the methods you have on your axis object, and they are grouped. You have the plotting functions. So there are even more than in this basic overview slide I've shown you. This overview shows the plot types, show the most important ones, but there are many more plots to add your data. And then you have all the other methods for clearing, changing appearance, setting axis limits, setting units. You can also explicitly add constructed matplotlib artists, and there is more other methods as well. So this is probably the most relevant entry point, and it's redesigned in the development version of the docs. So if you go to reference, then you have, first of all, you have both of the interfaces. You also have the pipplot methods here, which are also grouped like adding data and layout and the other things. But this is probably the go-to site for reference if you want to know what functions are there. There's a lot more interface, but all the other documentation of the API is much less likely that you need it. So these pages here are the ones that, if you want to look something up, you wouldn't want to go to these. So then we go to changing the appearance. What we've done so far, we could have used individual keyword arguments to configure our plots. But if you say you have a certain style in which you want to plot, that's maybe cumbersome because you don't want to change the line width for every plot you do individual. So what you can do is there's the configuration, which is called RC params. And most things of the plot are configured, the defaults are configured in there. So if I want to have a larger line width here, and the default is 1.5. If I want, so this would be the default plot. If I want to have a larger line width for all the plots, I could have used keyword arguments, but that's cumbersome. So I can make a global change to that setting. The disadvantage is it's a global change, which means, you see that below here, it affects all your future plots as well. And that's maybe not something you want. And it's definitely not something you don't want if you are a library author and you provide a plot, because you would change the default settings for your downstream users. So typically, explicitly changing this is not good. You would have to change that back. So you can, of course, do that, and then you're back to the default. Ideally, you would not hard code that, but read out the value. And this is a common pattern. If you do something, execute some code, and do some cleanup after that. In Python, we have context managers for that. Please show a hand if you know what a context manager is. Okay, so the idea behind a context manager is I have some initialization code. In our case, I set the line width. I do some arbitrary code. In our case, I plot. And I then have some cleanup logic in the end. In matplotlib, you can have a context, and that's the keyword for that is this width keyword. And the context abstracts away your initialization and your cleanup, and in between you can have arbitrary code. You most likely have seen that with working with files, because there it's the standard pattern. Typically what you should do if you open a file, you definitely want to close the file handle in the end. So low level, you would need to write it like this if you want to have correct code and clean up after yourself, but that's really cumbersome, and instead you can abstract this away, this cleanup into a context. So you have that's what's in here, and it works the same way for matplotlib. We have this RC context, and in the context block, I then plot with different parameters than in the rest of the library. So this sets the line width for this block of code, and afterward it resets the line width to the default. Okay, so just to show you, there are lots and lots and lots of configuration parameters. You can all look them up. If you have a set of these changes, maybe it's not so handy to always write a context for that. You can collect a set of these configuration values in a style sheet. There are some available, but you can also define your own. So, for example, this is the default style, and I can change the style to use the seaborn style, which significantly changes the appearance of your plot. And what's behind that is just a set of these configuration parameters. And as said above, global style changes are not so nice. Therefore, also for styles, we have a context. So you can say, I only want to plot this plot in the seaborn style, and after that I'll go back to the default style. So now that we basically know how to construct our figures and tailor them to our needs, let's look at how other libraries can use that, and how you can also use that to create simple functions to make your custom plots without having to write several lines of code every time. So there are some patterns how you can do that to write your own plot functions, and that's explicitly intended that you should do so. So if you have more custom plots, matplotlib isn't able to provide all kinds of variations of plots. you can and should write your own functions to handle custom plots. So, for example, I have here a data frame from a questionnaire, and there I want to have a nice visualization for that. I'll just show you how it should look like in the end. I should start at the top. Okay. I just changed this to a data frame yesterday evening, so So I want to have a plot like this. I have different questions, and people could give their opinion on the questions, and I have here 10 people strongly disagreeing with that question. And this is basically the set of data I have, and I want to be able to transfer this into this nice visualization. And this needs a couple of lines of code, and of course, in the end, I don't want to, every time I want to do that plot, I don't want to have all the lines. I want to just say, give me a plot of the survey plot of these data. And this is one way of making such helper functions, that you create a whole figure. So typically how you go about that is the inputs are your data, in that case my data frame. You can optionally have parameters to make it more customizable. I left that out here for simplicity. And the output, you typically should return the figure and the axis object you created in such functions, because that allows users, so if I remove that, that's my basic plot. That allows users to customize that further. For example, I want to have a title above that, then I can use the subtitle of the figure to add that still. So this gives people the opportunity, even though you provide a full plot, you can still customize it afterwards. There's, and we don't have to go into the details here. This is really the point of it, that you can abstract away the plotting details, and then when you deal with your problems, you just have your helper functions and call them and get your plots. The second kind of helper functions is if you don't want to make a full plot, but just want to have a more specialized kind of add this type of data function. And in the example here, I make a function where you have some data with some error band around that. And the typical way to go about that is you pass in the axis you want to plot into, and then you pass in all your data and optionally additional parameters. And essentially, this plot error band is just a wrapper about two matplotlib functions, the fill between function, which draws the area, and the plot function, which draws the line. And then you can use this also multiple times in the same figure. If I have two data sets here, I can plot them simultaneously into the same figure. And with the optional keyword arguments here, what you often do is just take the keyword arguments and pass them to one or sometimes multiple of the lower lying functions you use. And with that, for example, I can here configure the color for the individual parts of the plot. There's an alternative to that. If you are more into the pipplot-like interface, and if you don't want to pass the axis object here explicitly, which is sort of the way you sort of have to specify where your data should go into, you can make the axis object optional. Then, for technical reasons, you have to move it to the end because it's an optional parameter. And then you can use from pipplot this GCA means get current axis. And this is then a function which looks more like your pipplot functions, where you don't have any explicit axis objects, but you just give your data. So this is if you work more like with pipplot, you can make functions that look more like pipplot as well. Okay. Then I would like to have a word about how Pandas does it. Pandas has a bit of their own approach creating matplotlib figures, because they have a high-level interface, and the basic idea behind Pandas plotting is that they provide a full plot within one function. I just take a data frame. With pure matplotlib, I can here just plot the x and the y values. But in pipplot, in Pandas, you have this plot accessor namespace, and you can plot a line, and you specify the column you want to plot. The question is, if I do this, which axis is my plot going into? What's happening here? Because I don't specify anything. Is that working like pipplot, or is that something different? And the thing is here, in pipplot, what would happen is you plot into the current axis. If you don't have a current axis, pipplot will create a first axis and will use that from then on. With this matplotlib axis style, you explicitly create your axis, and with the Pandas plot style, they create a new axis for every command. So what you cannot do here, or not easily do, is if you say, I want to also plot B in here, you would get two separate plots. You can do that if you want to by adding additional parameters and passing in an axis object explicitly, but that's something you should be aware of, and that's also different from pipplot. The return values, the matplotlib functions, they typically return the created artists, so the line objects in this case, whereas you see it here, Pandas doesn't return the line object, but Pandas returns the whole created axis. So if you work with Pandas, it's really nice for some high-level simple plots, but it's a bit of a different philosophy than what matplotlib is doing natively. But what you definitely can also do is you can combine these. So this is what pipplot would do. If you want to write that out explicitly, this is what Pandas would do. If you want to write that out explicitly in matplotlib, you would have to do it with this, or similar also with the axis interface. You see that's much more work than having this configuration. So if you have data frames and you want to do quick, simple plots, this is definitely easier. You still can combine both worlds. So for example, if I plot my data, I still can take the axis object which Pandas has created for me, and then just work with the standard matplotlib axis interface on that, and I can annotate the data afterwards still. Okay. So Then I want to show you a nice extension or a nice application concerning animations. Maybe I first show you the result, and then I'll explain to you how. What you can do is create animations where you have the ability to have a continuous movie of your data in the Jupyter Notebook. And the thing to go about that is first, we basically have to create an initial plot. So this is the basic plot, and this is sort of the first image we want to have. What we then do is we save our created artists, so the line object and the text object of the title, because we want to access them later to modify them for the following frames. We then create a function which takes by default the index of the frame. You can pass optional parameters as well. And in that function, I can calculate some new data. And then I access this line object and set the new data to it. I can also do different things like changing colors and all the other things I can do. I can completely manipulate that object. And same for the text object. Here I set the text of the text to just show the frame number. And then you need the function animation from the matplotlib animation subpackage. And you pass in the figure you created. You pass in the function which modifies the artists you've created for every single frame. And you pass in this case, the number of frames, which is just 50 pictures. This creates the animation. We still have to get the animation to Jupyter. And to do that is we can convert the animation to HTML plus JavaScript. And then you have from IPython, you can embed HTML again. So you take that HTML that the animation generates and embed that into your notebook. So this is a bit of boilerplate, but the essential concept here is you create your first animation, you save all the artists you later want to modify, you define a function how you want to modify your data for each individual frame, and then you have this wiring up logic, and you need to close the figure, otherwise I can demonstrate that if you don't close the figure, you not only get the animation, but because the figure is still there at the end of the cell, a standard show is done. So I have the figure here, and I have the animation. And I just want to have the animation, so I close the figure before it's shown. So, and of course, you can do all kinds of things with that. You could change the axis limits, you can change colors. This gives you the complete freedom. And it's sometimes nice because you get the temporal degree of freedom to visualize some things which maybe don't work very well if you have just some static plots. And because you have the slider, you can also go back and forth and check individual steps in your animation. Okay, then we come to the last bit. What we've seen so far is basically static plots. I mean, we have the animation, but still it's not interactive. I can just have a series of frames which I can scroll through forward and back. And the inline backend, which we have used all the time, is basically generating an image, and this image is then shown in IPython, which means I don't have any access or any control over how which data is shown or which part of the figure is shown. There's another backend. So the backend is the rendering part in matplotlib, which is the IPython matplotlib backend. This is a separate package you have to install, so it's IPyMPL. And if you have that installed, you can, instead of matplotlib inline, you can use matplotlib IPyMPL. And that will then show you an interactive picture where you can go in and zoom into your data or pan around. And it also shows you here at the bottom, it also shows you the coordinate where your cursor is. So this is a bit of interactivity in that sense that you can focus on parts of your data. You can also look up single values. Yeah, you can save that to a file, but probably it's easier to just use savefig instead. And you can always switch back and forth between these backends with the matplotlib commands. So you can have the interactive one here, and then you switch back to the static backend and use that again. There's one fundamental difference between this approach and using really web-based visualization libraries like Bokeh and Plotly. And they have their advantages and disadvantages. So what we do here also in IPyMPL, the picture here is rendered in the backend. So for every step, you go to Python, and in Python you create a new image, and this image is transferred forward to the notebook and displayed. For Bokeh and Bokeh and Plotly, they work differently. They basically transfer all your data to the browser, and the rendering engine is pure in JavaScript, which has the following advantages and disadvantages. With these web-based visualization, you get even more interactivity. For example, you can do fancy things like you can click on this data, and depending on that, you have a plot to the side which reacts to that. You can do things like that in matplotlib, but it's really more difficult because you have to go back and forth through the back end. So if you need more interactivity than just being able to zoom in or look up a value, you better go to Plotly or to Bokeh. The disadvantage with these backends is if you have large data sets, that can become slow because you have to transfer all your data to the browser, whereas in matplotlib you just transfer the image. Okay, so that concludes the tutorial. I hope I have shown you some fundamental aspects and some ideas how you work with matplotlib, and you're welcome to still ask questions.
I have two technical questions. The first one is about comparing figures in unit tests. So it seems that the savefig method produces slightly different output on different machines. How would you compare the produced figure with some reference?
So there's a package called pytest.mpl, which basically does the hard work for you. So you have two modes of operation. The first mode is you create a hash value of your image, that you can easily store that next to your data. And the advantage of that is it's quite small. So you can make sure you still get the same image, but the disadvantage is if it's different, the hash value will just be different, you don't see the difference. The other option is that you create reference images and compare towards these reference images. What's typically a good idea is to remove text or at least reduce text, because text rendering is really a very subtle thing, because text rendering libraries do a lot of magic in subpixel rendering to get nice looking shapes on a fairly rough grid. And these engines tend to get different results on different operating systems, on different versions of these text libraries. So it's always a good idea to not try and compare the rendered texts.
Would vector formats in this case be better?
Yes, you can do that. That should work. You can just save it to an SVG. Yeah.
Okay. My second question is about support for concurrency in matplotlib. So if I need to plot, let's say, lots of figures, can I work on them in parallel?
That depends. So matplotlib itself is not safe for concurrency. But if you only produce offline figures, so if you don't want to show them interactively, then there's a way, and I think, I don't know if I can show it to you in the documentation later, but the basic idea is then you don't go through pipplot, which sets up all the machinery to make interactively and figure management possible. You can directly create a figure object and use the savefig method on that object to write it to a file. And this is isolated. This then doesn't interact with all the state and the global stuff. So creating a standalone figure object and using savefig on that should be safe to use in parallel. Are there more questions?
Any more?
So thank you for your nice tutorial. I have a very simple question. Among different interfaces with pipplot or Axis, which one would you recommend to use?
So if you just want to have it simple, just use the Axis interface, because that's the capable one and you can do everything with it. You can additionally learn the pipplot interface, which makes you a bit faster if you just want to have a quick look at your data. So are there still other questions?
If not, maybe Tim is around. So anyone has more questions, or we can stop here? Well, it looks like it's a right time to stop. So I would say let's give Tim a great applause for the great tutorial. We have half an hour break, I think. So, yeah. And, yeah, if you have any questions after, I think Tim is around and we'll be happy to answer them. Enjoy the conference.